But first of all, this is a poem I wrote about lab today. I'm sorry, it's awful. Don't react that way. You're only going to be disappointed. Roses are red, violets are blue. I'm going to Sycamore Flats. Want to come? It took me a long time to find the font and to center it. No, sorry. Anyway, it's kind of a poem. You guys ever think of like a chemical equation as a poem? It kind of, it kind of is. Balances it out. Yeah, right. It does balance it. Right, balance the cosmic balance. Although again, these equations are not balanced. So yeah. But anyway, sorry. I've so forget I said anything. Um, and before I forget, the technical deadline for your ecosystem processes paper is next class. If you want to stay on the schedule, which we've all been along. And I actually meant to ask, is that going okay? Are people, those of you that have delved into it, is that going all right? I hope, I don't know. Yeah, Olivia. Yeah, yeah. No, I know. That's great. That's great that you feel like it's not enough. That's great. That means you're a scientist. You demand more data. That's good. That you want to like see something quantitative. That is so awesome. So I mean, I mean, depending on what hypothesis we had, we could have used like a chi-square to compare proportions. We could have compared, but we've only got one sample from what was it, Sweeten Creek. So really, technically, we're not allowed to use statistics with just one sample, because most of our hypotheses are about the means, right? We would say like, you know, the amount of this like sediment particle is higher in this stream than this stream. And the way we would test that, certainly if we only took one sample, we would say, well, we probably don't really know. So what we do is we take multiple samples and then test for differences in the means with the assumption that the more and more samples we take, the closer we get to the true value, whatever that is. So with just the one sample, it's just kind of a qualitative analysis. So you'll just look at it and say, I realize there's only one sample from Sweeten Creek, but there's a heck of a lot more all these different particles. So we might say that it could be different potentially. Yeah. Really? So we have data in our Google Sheet for 2 from Sweeten Creek. Do 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 do. Do 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 do. Do 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 do. Do 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 do. Do 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 do. Do 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 do. Did um did I just what did I do? Sometimes I wonder about myself. Yeah. Yeah. So I think um You guys know what I did. Do you know what I did? Do you know what I did? What was just said. When I copied it over, I think what I did, I know what I did. I'm pretty sure that what I did is that I copied what was visible to me. And so I didn't grab those last two. So what you're going to want to do is, oh yeah, I wasn't super, yeah, that's not what I wanted to do at all. All right, so let's do this. Okay.
So now that we have two from Sweeten Creek, does that change the analysis you want us to do?
Completely changes it, Olivia. You'll be happy to know. No, I mean, I think. Yeah, and this is imaginary, right? These were fake numbers, of course. I'm like, why does that look so different? Just add the other ones on, and we'll keep it qualitative. Let's just keep it qualitative. Yeah. Because the problem is, if we were to, so what's the other thing we could do, right? So we could make the graph like this. Yeah, so really we've got 4 Beetree Creek and 2 Sweeten Creeks. So what could we do if we felt so moved to compare those? So I guess first step, I was even thinking more general like than that. Like we could just like average all the Beetree Creek ones and average all the Sweeten Creek ones to look at. But yeah, and so what that's going to do is it's probably going to give you more variation in the data at Sweeten Creek. We're probably going to have really high error bars because there's only 2 of them. We only have 2 estimates of the true mean. So, you know what? I'm going to leave that up to you because my instructions did not include doing that. Don't worry about the stats because with an n of 2, our statistical test is really not going to be powerful at all because if you know how statistical tests work, the more and more samples you get, the smaller and smaller difference you're able to detect. So we only have 2 samples. It's going to have to be a huge difference to be statistically significant. And maybe, I don't know, but normally you wouldn't even bother to run a statistical test with an n of 2 on one of them. So I'll leave it up to you. One option is to have 2 bars on each of these size fractions, right? One is mean and standard deviation for Beetree Creek. One is mean and standard deviation for Sweeten Creek. But you're also welcome to just do it like this and put each of the samples there. And either way, it's just going to be like a qualitative comparison. Like you're not going to do stats between them. We're just going to kind of eyeball it. What's that? No, you can't. You can, I mean, if you want to go there, that would in fact teach you even more because the mean is going to tell you more about differences between the sites, but showing the raw data will tell you just how much kind of variation there is in your data. So they each do teach you things. But for the chlorophyll, I do want y'all to do the t-test, right? Huh. And really, and that was with the like equals t-test parentheses array 1 comma array 2 comma 2 comma 2 and parentheses enter. That's weird. If yeah, yeah, if that's not working, it's probably, I don't know why that would happen, because the denominator should be the standard error, which shouldn't be 0. Well, anyway, has anyone, I'm not really expecting you to, but has anyone tried the t-test and had it work for them? Yeah, kind of, sort of, with the chlorophyll. I'll try it on my, did you? Okay, yeah, all right. Well, I'll try it as well, and if it's funky for me, yeah, because if it doesn't work on Google Sheets, it'd be weird if it works somewhere else. Because, so anyway, yeah, I'll check that and see what's going on. And there's a couple of t-test options, so it's possible that you asked me what the question was? Oh, James. Where did it go wrong? Where did it go wrong? Where did it go wrong? Anyway, so photosynthesis and respiration, we were talking about last time. I'm kind of realizing that these last couple of days, I don't know, it's kind of been sort of like similar in some ways. I might not spend as much time talking about stream metabolism next time I teach this class, but this is actually the last class that we're talking about like broad, like kind of stream ecosystem theory. And then next class, we're going to start on some like applied issues for the rest of the course, which is not that much, you guys. There's not that much left. But so we're going to start off talking about dams and talk about land use, invasive species, and climate change. So this is the last kind of stream ecology theory-ish class that we'll have. So anyway, yeah, we're just thinking big picture, right, about how ecosystems are affecting the just the functioning of ecosystem processes around them. And we talked about this idea that in streams, the only autochthonous production in this diagram of our energetic pathway is over here, whereas really everything else is respiration of carbon that's been fixed elsewhere. And so you might sort of expect, just from what we've talked about and looking at our food web, that there would be more going on here than here. And the paper that Torin led discussion on the other day indicated that in most streams, yeah, that's the case. Like there's a lot more of this going on, of like burning up carbon that originated elsewhere, than there is like fixing carbon in your own ecosystem. They're like, this is our own ecosystem, but we'll take all the carbon you can give to us and we'll use it up, because that's how we roll. So yeah, I thought Torin did a good job on the article from last time, but there's just a couple of figures there that I wanted to drill down in a little more detail, more than we would in like a 10-minute article discussion, because there are a couple of points I want to hit on. And so as was mentioned, like this is a study all across the US that looked at metabolism, and they used this like diurnal oxygen change method, like changes in oxygen level from essentially the lowest value, which is right before sunup, compared to the max value, which is usually like late afternoon. And there's just a couple interesting points that I wanted to circle back to here. So they looked at so these different sites all across the U.S. and even into Puerto Rico, and so really different ecosystems, right? Like Pacific Northwest. We've got some deserts over here. We got New England. We've got our neck of the woods, and we've got a tropical stream. And so it's kind of interesting to me that like they looked at this 0 point, which is where like respiration and photosynthesis are equal. And if we just look at a couple of these, so this is a creek out in Kansas. This is Walker Branch, not so far away. And this is the stream in Puerto Rico. What do you notice in the differences between these, first of all? So, okay, so we have the change over the 24-hour cycle. And then this is the net ecosystem production on the y-axis, right? And so 0 is the break-even point. So 0 is where your production equals your respiration, right? So I don't know, just looking at these, data, what jumps out at you? Like a scary Halloween costume. Yep, Kings Creek, right? There's only one stream here that actually is autotrophic at any point during the day, right? The others, Quebrada Bisley is consistently below, and Walker Branch, again, right around noon, early afternoon, gets close to breaking even and then drops down again. How do you think the riparian zone might differ between these three streams? Any thoughts? Mm-hmm. Absolutely, yeah. And why is that? Rainforest, yeah. And what about these data might suggest that? Yeah, exactly. There's no real increase in ecosystem productivity throughout the day, like we see in Walker Branch and Kings Creek. Here in Puerto Rico, it's pretty much constant. So yeah, I mean, the sun's coming up at some point in the day, but a whole lot of that light isn't hitting the stream there. And so that's, yeah, exactly the case. So this is Kings Creek out in Kansas. And so, it's like a lot of Kansas, there's, fairly flat, lower precipitation. So you don't get big forests regardless, but there's landscape alteration as well. So you often have farmland kind of right up to the riparian zone. I couldn't find a good picture of this stream. Like, I just really couldn't, but it looks pretty dense and it's so forested. Nobody can even get in to take a picture. This is a little bit of water. I don't know. Yeah, they said this was of that stream, so I just trusted them. But yeah, like dense forest. So, okay, so streams, right? Different depend on the canopy. So I just think it's important to realize, as the point was made last time too, that we talked about this ratio, photosynthesis to respiration, differing along the length of a stream, right, from headwaters to lower reaches. But again, the good old river continuum concept might not apply everywhere equally. And so there are going to be some streams that, just because of where they're located, is Quebrada Bisley, if you were to just look at these data, would you say that would be downstream, middle, or upstream in the river continuum based on this data right here? Any thoughts? Upstream? Y'all could say upstream and be correct. You could say way downstream and be correct, but you couldn't say the middle, and you didn't, which is awesome. Yeah. So the fact that there's all this respiration, it's, yeah, like an upstream, far upstream area where you're not getting a whole lot of primary productivity happening. Yeah, and y'all are right. Probably downstream, it would still be not respiration, but there might be a bit of a peak. Yeah. So more like an upstream, but in fact, the whole stream is kind of this way. And so I don't know. I just thought it was interesting, kind of matching these up geographically. So when we look at so two of the streams here out west, both of these had increases in diurnal production, and at times were autotrophic. So 2 out of the 1, 2, 3, 4, 5, 6, 2 out of the 7 streams were autotrophic at times. And then there were several of these streams that did have a diurnal increase, but were still heterotrophic. They never passed over that threshold, right? And then these two in Puerto Rico and then up in New Hampshire really didn't have much of a diurnal increase because of the canopy. So realizing that, like, land use differences among these sites and climate differences among these sites can make them look like they're in different parts of the river continuum, and really it's just kind of where they are, right? So they looked at photosynthetically active radiation as well and how it related to gross primary productivity. And a few different streams. So this is Walker Branch and Matt Creek in Michigan, Bear Brook, New Hampshire, Walker Branches in Tennessee. This is over in Kansas, Galena Creek. Where's Galena Creek? Oh, it was in, what's that, New Mexico, maybe? What do you think about the relationship between photosynthetically active radiation and gross primary productivity? If somebody were to ask you, like, I don't know, maybe me, what the relationship is, what might you say? Don't worry about the different colors in the circles there. I often wonder when I ask a question and wait for an answer, if people walk by, if they thought we were just like sitting here silently. Which is good. Like, it's good to be silent sometimes. Which probably makes you wonder why I'm still talking. Yes, James. Mm-hmm. Yeah, yeah. And what kind of positive relationship? Like South Kings Creek and Walker Branch? Positive, I agree. Like if we were to test the correlation between these two, like we'd find a positive correlation. But what kind of positive relationship? Malthusian? Yeah. The yeah, so it's the same relationship we'd see with like yeah, with like species redundancy and ecosystem function. It's it's an asymptotic curve. I didn't swear when I said that. Where it increases up to an extent and then levels off, right? So as we increase photosynthetically active radiation, it increases up to a certain point and then it levels off in these two creeks. Why might that be? What would cause our gross primary productivity to level off no matter how much more photosynthetically active radiation we hit it with? Say it again. Yeah, something else is limiting it, right? Nutrient limitation, where it could be um, um, something else that's limiting our producer growth. Exactly. And so what's interesting, so that's when we talk about like light saturation, that like when you get above a certain point, you know, you don't increase productivity. But look at Sycamore Creek. Linear increase there. We haven't saturated light at Sycamore Creek. Any idea what might be going on in Sycamore Creek? Wonder if it's the same thing at Sycamore Flats. Huh, didn't even think about that. Uh-huh. Oh, something so yeah, we could trace it back a couple steps in the chain. But there's something where there's more, probably more periphyte in there, right? Because yeah, so something else is limiting it here. So this is Sycamore Creek. And the important thing to notice, they looked at biomass of algae per square meter. And Sycamore Creek just had a lot more algae. And it didn't go into why that was, but there's just a lot more producer biomass. So maybe there was increased nutrients there. Maybe it was a bottom-up effect. Maybe it was a top-down effect where you didn't have the grazers limiting. But whatever it was, you know, the ability of these ecosystems to produce rapidly was dependent on producer biomass. And so when you don't have many producers there, you get to a certain level of sunlight, and those producers are doing all they can, right? But then in another area where you have a lot more biomass, then productivity ramps on up. Okay. So one of those streams, Bear Brook in New Hampshire, there's been a lot of really awesome watershed scale research done. And so it looks like this. It's forested. These are first and second order streams in this watershed. And a kind of interesting thing about this system is that it's underlain by impermeable bedrock. So when stuff goes into the water, it's not going to go down into the ground, right? So it's either going to wash out of the watershed or it's going to get transferred into, you know, carbon dioxide or producer biomass, consumer biomass, whatever it is. And so this is the area that was studied. So the authors, so again, first and second order streams. The watershed itself is a little bigger, but they looked at the small streams. And they had this thing called a weir at the downstream end, and it allowed them to measure the water, all the water passing out of this watershed. And so They had some settling ponds where they could get the organic matter. They did some crazy intense quantification of ecosystem properties. You could really do some detailed measurements to see just what this watershed was doing on the landscape. Like, what was it? How was it affecting these inputs and outputs? And just as an aside, this area has also been used after that earlier study to look at effects of land use change on streams. So for instance, they clear cut this small sub watershed in the area, and they looked at how it affected stream chemistry. And so, for instance, one of the things that they found was that after deforestation, there's this massive nutrient loss out of the watershed, because there's just so much more erosion. All the stuff that's in the soil is brought in. So these kinds of watershed scale experiments have also taught us a lot about anthropogenic alteration, because it allows us to do these large scale controlled experiments, which are really hard to do. All right. The first time I looked at this figure, my brain stopped working for a little while. And it kind of blows my mind. And then the more I look at it, I'm like, huh. Then I look at something else, and I'm like, Then I look at another, I'm like, what? And then it's like, no. So they were able to quantify all of the energy inputs into this watershed. Again, like this is the kind of, like, you have to live your life like out at this watershed to collect this kind of data. It's crazy. So they had data on all the inputs into this watershed, all the outputs. And so it's in kilocalories per square meter per year. This is nuts, you guys. So the inputs are here into the watershed. And then this is kind of what's stored in the stream, if that makes sense, for the short term at least. And then it's output over here. And so, like, I don't know, just so each of these little compartments has a number next to it. And I don't know, I guess I'm curious, first of all, are there any numbers? And so this is relating to essentially the carbon flux, right? The energy flux of a small watershed. Is there anything that strikes you about this figure besides how much work went into getting every single one of those numbers? Gosh. Yeah, Brian. Yes, and that's the mind-blowing part, right? That literally they had to quantify all of this. And so yeah, so all these different inputs from all these different sources, all these different outputs, it all had to add up. It had to, right? Because otherwise it's like, what are we missing? Yeah, right? This was one of those papers that somebody had to do it. Like, I'm glad it wasn't me, but somebody had to really test these ideas. And this was published before the river continuum concept, right? It's cited in that paper, but so this was the early 70s. So people were kind of like, wow, okay. Didn't know that about it. So yeah, absolutely. So they're able to balance this, which is like maybe the first amazing thing. What if we look, and so you can see they looked at input and they broke it into allochthonous and autochthonous. And what might we say about the energy input into this system? So much more, a ton more, right? So if someone has a calculator, you could do the math, right? 6,000 related to 10. What percentage of 6,040 is 10? The answer is hardly any. No, I'm not sure. So almost, right, almost entirely. So this is one of those first papers that they're like, yeah, this ecosystem is almost entirely dependent on input from outside. And then so they're meteorologic and geologic. So meteorologic are things that are washed in with the rain. Washed in with the rain, carried down the stream. Geologic is stuff that's dissolved. It's carried through the water. So you can see kind of similar there. But again, we see the importance of leaf litter, but also a lot of dissolved stuff coming in. So just thinking big picture, then if we kind of move through here in a second, think about outputs. you know, geologic was about twice the same as biologic. And the way they defined it, geologic was organic matter in the stream flow. So this is stuff that was in the water leaving the stream, if that makes sense. Everything else was heat loss through respiration. So all the consumers, right, that are eating up these carbs and metabolizing them, that energy is leaving through heat, though. Those things were being consumed. Now, okay, they probably didn't talk about, there might have been, I don't know, maybe there were some birds that came down and ate some invertebrates and left the watershed, but hardly any, right? So most of this production was staying in place, right? So these leaves, all of these macro invertebrates and micro consumers. So really, a couple main points. Again, almost completely allochthonous, right? Producers are not doing a whole lot. And it's also interesting to me, again, remember we said how important dissolved organic matter was? That it's the largest pool of carbon in the ecosystem. But what's the problem with dissolved organic matter? Yeah, it's hard to uptake. It's kind of like if you're in a stream and you're trying to catch fish, but the only net you've got is this big old net that we have in room 135 that someone bought a long time ago to do a study on turtles. And the mesh size is like this. And you're like, there's all these fish. Oh, but I didn't catch any. Oh, I didn't catch any. That's what it's like. Like this dissolved organic matter, it's the biggest pool of carbon in the system, but most of the consumers can't use it. But just to review, how does it get back into the food web? Bless you. Who can take it up? I mean, who? I mean, they might not consider themselves people. Their brains are not like ours, but. So the myofauna help get the energy to the other food web. What were you gonna say as well? So filter feeders can get this stuff and some. So like freshwater mussels can get some of this stuff, but most of, and freshwater mussels, you're gonna find them more kind of in more like downstream areas where there's like lots of fine substrate. So most of this, it's even gonna go through the filters of our black fly larvae and our caddisflies. Like it's gonna go through. They're gonna be so frustrated. They're like, I didn't catch it. But it's going to get taken up by microbes on biofilms. And remember, that's the peanut butter on the leaf cracker for the invertebrates. So, you know, this is the output, right? So this stuff is leaving the watershed, right? This is the output. But in the stream itself, that some of that dissolved organic matter, it's going to be taken up by microbes on these biofilms, and then again ingested. If it's on a leaf, it can get ingested by the shredders as they're eating it. But if it's on a rock or something like that, that's where the myofauna are going to help to get that energy cycled back into the macro food web, because they're going to be feeding on the tiny microbes there in that biofilm. Did I tell you the story about my son and the names which you don't ever hear spoken, so you're not quite sure how they're spoken? Yes. Those things as well. The amobas are going to be there in the biofilm eating things, and then some of the myofauna will be eating them, and it moves it up. Yeah. So again, more carbon than anywhere else is going to be dissolved in the water, in organic carbon, right? So stuff that, yeah, that can be usable. It's not just like CO2 or something. All right, so I don't know, man. We could do like a whole class on this, like figure. It kind of blows the mind. But to me, the main take-homes are, again, the importance of that allochthonous input, that we have about twice as much leaving the watershed as we have being processed through our food web and taken up and lost through heat. And again, this dissolved organic matter. Big source, but it's not as easy to use. FPOM is probably the easiest to use here because someone's got to break down CPOM. But again, what happens to the nutritional value of our organic matter is it gets processed smaller and smaller. What happens to the nutritional value of organic matter as it gets processed more and more? It goes down, right? So yeah, so you know, CPF, FPM going down. All right, cool. Anyway, and so just looking again, looking at a lot of the same sites that the Mulholland paper et al. Studied, are the paper that we were going to discuss for today. Looked at a review of carbon budgets for streams all over North America. Here's Bear Brook, New Hampshire. So this is the one that we just talked about, right? And they grouped all of these streams based on a couple things. The first was relatively low transporting of carbon out of the watershed versus relatively high. And they also found that another thing that distinguished these streams was the amount of leaf fall. So some that had low, some that had high. And as you might expect, again, the RCC, the streams that had the highest leaf fall had lower rates of gross primary productivity. Those at lower leaf fall had higher rates. Yeah, so this is just probably we're getting kind of, you know, toward larger streams that aren't as tightly connected to the riparian zone here, a little more open canopy. So yeah, so I mean, I think the main point here is that like these small mountain streams, like where we are, so these are streams in Oregon, Quebec, North Carolina. Although I'm not quite sure where that one is. Right, streams in these mountains are characterized by relatively low transport of carbon out of them, but also fairly high leaf mass, low GPV. I don't know, maybe this is common sense. And then, you know, arid streams to the desert side, as you might expect, you know, high rates of productivity, relatively less leaf fall. This benthic organic matter, I guess you'd expect that too. Where you have lots of leaves coming in, you've got lots of organic matter in the benthos. I don't know. Just making the point that not every stream looks like Bear Brook. I mean, so that's when we studied in so much detail, but then looking from place to place, you know, you do have ones that have higher rates of productivity. So it's not all going to be less than 1% autochthonous.